All right. Hi, everybody. So welcome to VSA webinar. So today we have a shifted version, shifted webinar in time. But after today, we resume our two fortnightly events. So the next webinar will be on 15th of March. I'm happy to present Alexey Kovalev. He's a PhD student at HSE University in Moscow, Russia. And he will be presenting his research on using vector symbolic architectures for tasks of visual question answering. So without any further delay, so I leave the floor to Alexey. So he will introduce further.
Thank you, Evgeny, for good introduction. Hello, everyone. I just say it again. My name is Alexey Kovalev, and I'm pleased to be here and present to you our work, which is done with my co-authors, Mahmoud Shaban, Daniil Kirilenko, Evgeny Osipov, and Alexander Panov. And the title of this work is Combining Vector Symbolic Architecture and Semiotic Approach to Visual Question Answering. And at the beginning, I'd like to introduce you to the task of visual question answering. Give me a second. One moment. I have some problems. Okay. Yeah, so it's right. In this task, the system, AI system, given an image and a question in natural language, should give you an answer. The questions may be different. The images may be very difficult to understand even for a human. And there's several common data sets in this area. One of them on the left of the slide is called VQA, which stands for Visual Question Answering. And this is, I would say, the most famous data set. And it's very difficult in terms of images and in terms of common sense reasoning, because if you look at this example, for example, here, where we have a pizza, and the question, is this a vegetarian pizza? The system should have a knowledge of vegetarian. And maybe on this picture, the system should understand what means 20/20 vision. But on the other hand, there are data sets which simpler in vision, in visual part, but still very interesting and quite complicated in reasoning tasks. On the right side of the screen, you can see an example from Clever dataset. And this is a synthetic data set, what was generated in Blender engine. And nevertheless, it's synthetic. It's still quite difficult to answer for us human, because if you consider this question, what size is the cylinder what is left of the brown metal thing? It is left of the big sphere. So it requires like reasoning, about relations between objects, and we're not able to answer this in like immediately. We have to think about this picture and like find this big sphere, then brown metal thing, and just cylinder, and so on. And another interesting property of this data set, so it's called diagnostic, because the authors of the data set eliminated biases about questions and images, because the usual problem with VQA task that system can answer questions without looking at the image. If you have a question, what is color of a plate on the table? So the system just can say white, and this will be a right answer for like 90% out of 10, out of 100. So in these data sets, the questions and pictures are balanced. So the authors propose it as a task to diagnose system how well they work on VQA. And if you take one step further from this visual question answering idea, we can finish at a habitat challenge. That is challenge and data set with the same name. That consists of a scene for a robot. So it's a real environment. So this is the pictures that were taken and constructed environment from this. And in this task, the agent placed at random point in the scene, in the environment, with random orientation, and is asked to find a specific instance of some type of objects. It could be chair, sofa, or whatever. It should find this object and navigate to it. And the type of questions asked in this challenge are quite simple. But if we extend these ideas about the navigation of an agent in the environment and extend it with more complex questions and more complex reasoning engine, then we can finish in something that's called embodied AI. So then our AI system, not just like a computer program, but it has like its representation in a real life, in a real environment. And this is something that is called like cognitive robotics, and or maybe and even like cobots. Yeah, that's not for cognitive, but for collaborative robotics. What could assist people in the like usual tasks. But when we try to solve this kind of problem, there is another problem that appears, and this is called the simple grounding problem. And my main point here is how an agent represents its internal knowledge about concepts in environment. So the agent has to refer somehow from this internal representation to real objects on the one hand, and on the other hand, then he or she referred to this real object. It has somehow to understand what it could do this particular object. So how it can be used. And one of the approach to solve this grounding problem is apply semiotic approach. And semiotic approach grounds in the work of Soviet psychologists Lev Vygotsky, Alexander Luria, and Alexey Leontiev. And first two of them proposed a theory called cultural historical psychology. I just read some of them, the statement, and like apply it to robotic area. So first of all, they say that social environment is the main source of personality development, and this means that if our agent operate in coalition or in a group of agents, or maybe interact with other agents somehow, so this could be an opportunity to improve agent by itself. Another, that external activity and culture tools or subjects, as many collabs, interest in the internal plan of here's of human, but in our case, in agent. So this means that then agent interacts with environment or with other agents. So at the end, it could replenish its own like understanding of the environment it works with or about agents. And another idea that consciousness develops through the dialogue. And again, this means that our agents has to interact with these other agents. And like in case of like cognitive assistance and assistance robotics with people as well. And another tool that we use, it's activity theory. It was developed by Alexey Leontiev. And he said that humans actions are subject, and the main here is the goal. So actually, like any activity need just to like to achieve some goal. So we can look at activities as an object by itself, and we apply it just we apply it when we want to achieve some goals. And when I talk about semiotic approach, there's like trade-offs between semiotic and symbolic approach to tasks. And compared to the symbolic, we need to have several properties to call the system semiotic. First of all, we have a special type, it's called name, that help us to distinguish one piece of information from another piece of information. In case of symbols like named by themselves. So the symbols and names like glued together. But in semiotic approach, you have to have this distinct tag, it's called name. Also, information must be structured. So there is no just separate piece of knowledge. They should have internal structure, and also they have to be connected and combined into a network. So they should relate to others, notions and other information that agent is known. Another idea that any piece of information, as it has internal structure, could be decomposed into its part, and then we can have ability to look at the same piece of information from different level of abstractions. And that depends on our current task at the hand and what we want to do with this. The main component of semiotic approach is a sign. So it's a special structure. So because, as I said, any piece of information has to have structure. It's composed of this tag that's called name, already mentioned it, and three other components: significance, meaning, and image. And the idea behind these concepts is as follows. So significance, that is something that shared among, like knowledge that shared among the coalition of agents or group of agents. And if say some like example from real life, if we'd like to call the sign for a book, so the significance would be read book or buy a book. And meaning is something that agent develop through interacting with environment, and this how experience works. And in some cases, you may read book, or maybe you would like to candle fire this particular book, and then this will be meaning for you or our agent in this case. Image could be considered as a description of our object that helps us to distinguish one sign from another sign. And in this case, like a book has cover, paper, pages, and this is like distinguishable features of this particular entity. And also each sign, like all signs, are interconnected into a network, and we call this network a semiotic network. And this is what we work with. So this the main like storage of knowledge of all agents. But how we are going to represent these components? In case of images, we represent each component as a collection of causal matrices. And causal matrix is just simply a matrix, and in this simplest form, it will be a binary matrix. There, each column corresponds to an event in time, and each row corresponds to feature. Then, if you have one particular place in this matrix, that means that this particular feature appeared at this time event. And each of this one, it's not just a number, it's a link to another sign. So this is how they interconnected into a network. And with this particular structure, we can represent not just objects, but actions as well. And then we have to split column indices into two parts. First parts will correspond to causes, and another parts will correspond to effects. And there is just assumption that every effect appears after like every cause. But in like simple situation, when we operate with just objects, we don't need this separation of indices and just work with a normal matrix. Let's look at an example how it works. Assume we have to recognize the face on a picture, and we do it by recognizing its parts. And in this case, we recognize first, first left eye, then right eye, then nose, then mouth, and we have these time events in our causal matrix, and these corresponding rows for these features. And we end with this diagonal matrix. But it may happen that our system recognized this part in different order. So first right eye, then left, then mouth, and then nose. And when we end up with this matrix, and this matrix is actually identical up to permutation of columns, and they correspond to the same sign. In this particular case, it's a face. So we organize these matrices into tensors, we call causal tensors. And here by tensor I mean just a multidimensional array, three-dimensional in this case. And then we have already this like two known dimensions for events and features. And also here we have this third dimension for precedence. But there is a problem with it, because if we increase the number of features, so then the number of precedents increases n factorial. So the richer the description, the bigger number of precedents we could make. And this is undesirable behavior for our system. And now when we know how this works like for one object, let's have a look how we can organize it into hierarchy. So first we have this raw input signal, so basically this picture. Then we have some feature extractor that helps us to find this like smallest atomic pieces of information, and they could be used any feature extractor. And further we will see that in our case we use neural networks, convolutional networks to be correct. And each of these part corresponds to its own sign, its own image component of the sign. It's called left eye, right eye, nose, mouth. And they, by themselves, part of a sign is called head. And on the next level abstraction, head is a part of body. And of course, body has another parts. So there are other signs that connected to this sign. And then we end up with this causal matrix on images, causal network on images. And now we are ready to formally define the sign. And but before it, we have to I have to say about linking functions. With functions that helps us to move from one component of a sign to another component. So we can move from name to image, from image to meaning, and from meaning to significance, and we can move in another way. And then we assign the tuple of four components, name, and corresponding causal tensors for images, meanings, and significances. And such that if we apply combinations of linking functions, starting from maybe this tensor, we apply combination and we end up in the same tensor. So the sign is a stationary point of composition of these linking functions. And this helps us to connect these 4 different causal networks on each of component that then form the network, what is called semiotic network. And this approach is already used in several applications. And here I just briefly explain several of them. Here you can see the problem of navigating robot in the environment from a starting position to the goal by using the so-called pseudo-physical logic. So our agent doesn't know anything about absolute coordinates of its position or table is a cube, but it knows about relations such as above, below, left, right, farther, closer, and so on, and like far away, nearly, closely, and then agent is able to move from from starting position to the goal. Another example is a well-known block world where you have to plan how to construct a tower of cubes. And the third one is smart relocation tasks, where we have a coalition of agents, and the goal of these agents to move to this area. But there are obstacles on the way, and one of these objects is able to move these objects, to move these obstacles, and another don't. So they should like work in coalition to help each other. They try to plan this path, but then they have to understand that there is no straight path through these obstacles, find the block that is movable, split roles between agents who will be move this block, move it, and then plan again to achieve this area, to go to this area. So in this task, this semiotic approach is successfully used, and in our case, we want to apply it to visual question answering. And we not just want to apply it like by itself, but we'd like to use the property what VSA gives us, and we can use it in our approach. As I said, the STEN is represented like hierarchy, we represent knowledge hierarchically, so they can give a description of a STEN in hierarchical way. So they have STEN, object in this STEN, the attributes, and the values. But as I said, the problem with this matrix is that you have this third dimension that grows with number of features, and also we have this like matrices which corresponds to the same sign, but they're different in their permutation. But what if we use we represent each of these columns as a hyperdimensional vector? Then we can apply bundling to these vectors to compress this dimension and obtain just one HD vector for this particular matrix. And then we can apply binding operation that helps us to build this hierarchical structure. So we will use binding to move from one level of hierarchy to another, and we will use bundling to compress our matrix into one vector. And in our particular case, we used polar vectors, this dot product as a similarity metric. So this is like the high-level idea what we want to do. And also we were inspired by a very interesting work It is called like narrow symbolic UKA, and they use this interesting approach. Then they disentangle the reasoning engine and scene and question representation. So they used like convolutional neural network to represent this scene as a table. So it's basically like a data frame. And also they used an LSTM encoder to represent question as a program that could be applied to this table. And actually, each line in this program is like a filtering function. That's like as you work with pandas and data frames, you can work with this representation of scene and this program, and they get the answer at the end. The interesting point here that they used very very interesting approach to train this part. So this is quite obvious idea, but here they pre-trained network in supervised manner for 300 questions, and then they fine-tuned the encoder with reinforcement algorithm. So what they done basically is that they input the question, translate it into a program, apply this program to the scene representation, and then they got an answer. They compare it to the ground truth, and if it's if true, yeah, then add one to the reward of the system, and then they average these rewards in batch and use it to update weights of encoder. So this was trained like in reinforced manner. And we were inspired by this work, but in our case, we want to exchange this part with vector symbolic representation. And we end up with our architecture. There we represent scene as a vector, as a HD vector, and apply programs that works with HD vectors to our scene and extract the answer from this representation. Also, we did several modification of the original architecture, and they used. Just go to the previous slide. Here at the LSTM level, they used one head at the end, and they predicted filter-shaped scene cylinder as a one token, function and its attributes. But we predicted separately function and the attributes that helps us to comprehend the dimensions, because if we increase number of functions, we have to increase number of outputs of our head. But here we simplify this problem. And our scene represented as follows. So each object represented as a bundling of attribute values pairs, and there each attribute value is an HD vector. Then each scene represented as a bundling of objects binded with their representation. And I'll just explain a little bit closer on this toy example. There we have this simple scene that has three objects: circle, square, and triangle. And we have just one attribute for each object. It's its shape. And here we have HD vectors for shape, attribute for the values, and also we have HD vectors for positions of these objects on the scene. And so here we bind shape its value circle, bind the special ID of this particular object basically HD vector as well. We do this for other two objects, and then we add here the description of positions of this object on the scene, apply bundling, and then we got this whole scene representation as a one HD vector. And now, when we have this representation, we are able to apply these small programs, small steps in our programs that answer the question, and several of them. And most basic procedures with given attribute and value pair returns objects with this attribute and value. And here, first of all, given attribute and value as a name, as a symbols, we extract the RT vectors from item memory, then then bind them together and get attribute value vector, combine it with this scene representation, and find and get the noisy version of a vector which is close to objects that have this particular attribute, this particular value of this attribute. Then we query the item memory for these objects, and if the similarity between this noisy version and given object is bigger than some particular threshold, we add it to a list of results and return this result. And this is how we obtain objects with particular attribute and value. And also we can get a value for a particular object given an attribute. So here the procedure is almost the same. So first we get HD vectors from item memory. Then we construct this pair by binding object vector and attribute vector, bind it with a scene vector, get noisy version of value vector, find the closest vector in item memory where we store these values, and return as a result. And applying these procedures as a programs, we achieve following results on Clever dataset. So there are several types of questions in Clever for existence. So if there are any objects on the scene, for counting, so we may be asked to count how many objects on the scene. We may ask to compare either bigger, which number is greater, like for these objects or for these objects. Then we can query the attributes and compare other attributes have the same value. And on two types of questions, our system at this particular stage achieved almost perfect results. It's almost it's about 0.997 accuracy. But on the other questions, we have not so distinguished results, but still they're better than the random choice, and we will be able to improve it. And in this particular plot, you see the dependence of accuracy for each type of questions versus HD vector size. So we use quite big vectors. And now we can this is our current work, yeah. But also we have in mind the work that extend this approach further, and this is actually what I talked about at the beginning. So if you consider the cognitive robot, we collect a data set. It consists of images from habitat data set, but we asked people to ask questions about these pictures here, and we collected it. Now it's available through this link, so you can follow it and download the whole data and the equations. And this will be a good platform to start with development of embodied AI. So then we have this cognitive robot, which is able to navigate through environment, interact with humans in natural language, and answer questions not just about images as in VK or synthetic sense as clever, but even about real flats, real environment we all live in. And as a conclusion, I would say that in our results, we have a working pipeline for VQA task. And in this pipeline, we successfully combined VSA architecture, semiotic approach, and neural networks. So this can be viewed as a neurosymbolic approach together, I would say. And our primary results not so bad. There's, of course, space for further development, but even now they're quite good. And there's great potential to extend this approach to other tasks such as navigation, loop closure, and visual common sense reasoning. And to check this, to check these approaches on these tasks, we collect this data set, this environment images, and also the challenges. So first of all, we'd like to achieve comparable accuracy to SOTA architectures on the one hand. On the other hand, apply this approach to more complex data sets. So how we could apply this not just to these syntactic images, but for the VQA dataset by itself. And other question, what if there are more than 10 objects on this channel? Or maybe that 100 of objects? Will we be able to use the same VSA plus semiotic approach to solve and to have a description of this channel? And even more, if there's not just few features for each object on the channel, but again, like tens or maybe hundreds, will we be able to deal with these kind of situations? And that's it. Thank you for your attention. Just finish on this slide.
Yeah, thank you very much, Alexey. Thank you for the great talk. So now I open the floor for questions, if any. So please unmute yourself and speak up.
Hello?
Yes? Maybe I can start with the first question on my own. So this scene representation. So we all know that when you bundle together many objects, so there is an issue with capacity of HD vectors, and obviously, so not very great accuracy can be attributed to the capacity. So how do you think to overcome this problem?
Well, really, this is the challenge I mentioned on this slide. So if we increase the number of objects, we will be able to use the same approach. And well, of course, we can increase the number, like the HD dimension of the vector. But as you see, like in this on this plot, it helps, but not too much in our particular case. And so we can finish at storing, because now we store just like atomic vectors for attributes and its values, and the final scene vector. But if we will store these intermediate results, maybe vectors for objects as their descriptions, or maybe some parts of them, then I think we will be able to increase capacity in terms of objects on the scene.
Okay, good. Any more questions from the audience?
Yeah, I had a question about so how does the performance that you're seeing compare to other systems that are applied to this same data set, the Clever data set?
Thank you for your question. Okay. So for this particular type of questions, we get comparable results. So it's the same as for example, this work with narrow symbolic VK. But for other types of questions, we still have to increase our accuracy. So for these types, yeah, it's fine. It's like sort of results, I would say. But for this, still no more.
Maybe you can spell out. So what types of questions you have problems with?
It's problem with counting questions. Well, usually it's normal problem with VQA datasets. So and with the VQA systems, they usually better at counting, and also with let's check these existence questions. So then the question is kind of either an object on the same size as like a metal sphere on the left or the right, on the small rubber cylinder, for example. So they could be such complicated. And another problem question is like query accuracy. Then we query some particular attribute. This is now the most problematic questions types.
So basically, whenever you need to extract one or several properties from a bundle, then you obviously have problems related to the capacity.
Yeah, so yes. Because as you see here, there's like compare num accuracy, compare attribute accuracy. We are good on these questions, and the data set constructed in the way they have two types of questions. First one is like a linear, and another one is like more tree-like. They have two paths, and then the question is like linear. They have like more procedures on the stage, and it's like difficult to get the right answer at the end because we have to filter send for several times.
So how should I read this chart in showing the accuracy compared to other systems? Do other systems get an accuracy of 1 so that the exist accuracy here is like 0.66 compared to other systems getting 1 or what?
They got close to 1, so like 0, 96, 97, so 99 and 6. Yeah. But also they have this, for example, in for this particular architecture, they have like the deterministic approach, and we still have some randomness in the encoding. I mean, it's maybe not like, yeah, how to say, not a lot of process what we lose here, but it's still like much the representation here is much simpler, and it's they got this like points in accuracy much simpler as well, because here's just like normal like data frame as in pandas, and they just filter it. Okay, let's put here.
All right, Ross, I see you raising a hand.
Thanks for the talk, Alexey. About 1/3 of the way through your presentation, you were talking about the tensor representation of signs and how their components are related to each other. and you're talking about there being a stationary point relating those components. That's the one. Yes, thank you.
Yeah.
And that's, I think, is before you start talking about VSA. So you're back in ordinary maths domain at this point. Does that stationary point relationship play any role in the dynamics of your VSA implementation, or is that just a fact about the about sort of the mathematical origins of these?
Not in our case. We use just image component of a side, so we don't use the whole like structure. So and then it's this particular property doesn't matter. I mean, this is just high conceptual working.
Okay.
Efficient.
Thank you.
Thank you for the question.
All right. Maybe we have time for one more question, if any. Well, if not, then I thank Alexey once again for the interesting talk. And thank you all for attending this webinar. So I want to remind you that the next webinar will take place in 2 weeks from now, on 15th of March. So please have a look at the schedule on the website, VSAONLINE. So the talk will be given by Dominic Vidos. So with this, I want to end this webinar. So once again, thank you very much for attending, and see you next time. Goodbye.
Thank you.
Bye.
Goodbye.
Thank you.
Thank you. Bye-bye.
Thank you, Kenny.